All right, gang, whiplash. A little under tempo. Tomas, just do your best. Little trouble there. It's okay. Let's pick it up at 17. 5, 6. Not quite my tempo. 5, 6, and. You're rushing. It's okay. 5, 6, and. You're dragging now. You're dragging. It's okay. 5, 6, and. Were you rushing? Were you dragging? Or are you gonna be on my f***ing time?
Is this you? Have you ever been sitting at a party wishing you could finally impress someone? Everyone has their cool party tricks, like juggling or shooting pool really well.
Even if you don't have any natural talent, there should be something for you too.
Remember that time when you finished washing the dishes from your dinner party and your wet finger rubbed against the rim of that glass just right, creating that slightly wonderful sound?
It was hard, wasn't it? Getting that angle, getting that right note. Do you wish it was simple and consistent and maybe good enough to produce more than one note?
Well, we have the perfect solution for you. The perfect glassware for acoustic behavior and your drinking desires. Introducing the Resonance Collection.
Our product line offers a variety of glassware, from the standard for your everyday drinking needs, to the coupe for serving up your fancy cocktails, to the burgundy for your light-bodied reds, to the sherry for your fortified wines and liqueurs, and even the champagne flute for those special occasions. Each and every one designed to produce the best set of harmonics for you to impress others with your musical talents at the next get-together.
But why should you believe us? Why should you believe that the Resonance Collection is any better than a normal set of glassware? Well, to break that down, why don't we actually talk about what's happening behind the scenes?
So when you rub a wet finger on the rim of a wine glass, the friction force from your finger is vibrating the glass, exciting the natural vibration modes of the glass.
Every glass has its own preferred ways that it likes to vibrate, called its eigenfrequencies, which depend on the glass's geometry, thickness, material, and even how much water is inside the glass.
When the frequency of your rubbing matches one of these natural modes, the rim of the glass begins to oscillate strongly, creating a strong, sustained tone.
What makes this so difficult with an ordinary glass is that most glasses aren't designed for acoustic performance. Small variations in shape and thickness can shift these natural frequencies, which can create unpleasant tones.
That's why we used advanced multiphysics to understand how the glass vibrates in 3 dimensions, not just one note, but the full spectrum of resonant frequencies that give the sound its character and richness.
By carefully tuning the geometry of each glass in the Resonance Collection, including the bowl width, the rim shape, the overall height, and the wall thickness, we were able to engineer glasses that will produce strong, harmonically rich tones.
So in other words, we didn't just design beautiful glasses, we designed instruments disguised as drinkware.
We started the design process with a simple, standard wine glass. Every shape of wine glass has smooth walls and a smooth bowl shape. This was made in COMSOL, using an interpolated curve on a 2D plane. Different points on the curve were parameterized, like the maximum bowl radius, the rim radius, the thickness at different parts, and more. No matter what values these parameters were given, the interpolated curve would connect the points smoothly to create the cross-section of the glass. This cross-section was then revolved to create the solid 3D wine glass you can see here. Instead of painstakingly, individually designing every single glass, we cleverly designed the parameters so that we could use a single model and extrapolate it to any shape that you can imagine. By adjusting certain ratios in bowl radius to height, the complete range of glassware was produced from a single template. After creating adjustable domains for the air and water inside the glass, we could start implementing the physics and boundary conditions.
We applied solid mechanics physics to the glass domains, which accounts for the response to the applied load. We assume the bottom of the glass is fixed to the table, which isn't totally realistic. However, it won't greatly impact the eigenfrequency results. We then considered the pressure acoustics, which were applied to the water and air domains inside the glass. At the interface between the glass and the stuff inside the glass, we applied an acoustic structure boundary, coupling the physics of the two domains.
Of course, no simulation is perfect. Our model assumes ideal material properties, a fixed base as previously mentioned, and simplified fluid behavior inside the glass. In real life, hand pressure, imperfections in manufacturing, and room acoustics would all affect the final sound. But importantly, these assumptions don't change the design trends that we found. The geometry that improved harmonic richness in simulation will still guide better real-world designs.
After all that, we were ready to start testing out hundreds of variations in geometry, looking for optimal acoustic behavior. But what even defines optimal behavior?
When you perform an eigenfrequency study, the results will give a spectrum of eigenfrequencies corresponding to their natural modes within the glass. And the more well-distributed and defined these modes are, the more musical and richer the sound will be. And this is what's going to help you impress people.
So in ideal systems like a guitar string, all these eigenfrequencies are multiples of the first frequency. So here the first frequency is 110 hertz, the second one is double that, the third frequency is triple the first one, and the fourth frequency is quadruple the first one.
Wine glasses are much more complex than a basic guitar string. So for our study, we don't expect the frequencies to be perfect multiples of the first one. However, if the higher eigenfrequencies are close to ideal, then that's a good sign.
So now that we have a way to quantify optimal behavior, we can analyze hundreds of different wine glass shapes. Of course, we're not going to do this manually, so we use the parameter sweep function in COMSOL to sweep over multiple different parameters of the glass's geometry, the material of the glass, and the water level.
So after each parametric sweep, we would take the COMSOL results and export them into Excel for analysis, and we'd be looking for ratios that are close to the ideal integer multiples between our different frequencies. And we would do this for all the parametric sweeps, and we would determine which set of parameters gives us the absolute ideal glasses for the resonance collection.
So we've combined the elegance of fine glassware and multiphysics engineering to create something that nobody else on the market offers. With that, we're asking for $100,000 for 10% of our company. With that investment, we can move beyond simulation and bring the resonance collection to life.
Your investment isn't just limited to consumer glassware. The engineering behind the resonance collection opens the door to a much broader design space. The same multiphysics optimization approach we used here could be applied to acoustic ceramics, luxury tableware, and even custom designed instruments or architectural pieces where sound quality matters. Anywhere that shape, material, and vibration interact, this type of simulation-driven design can create products that are not only visually appealing, but also perform in ways traditional trial and error design can't achieve.
Imagine walking into a party, running your finger around the rim, and instantly impressing everyone in the room. Invest in resonance, where engineering meets elegance. That is my tempo.
Throughout the course of this project, we used generative AI to assist us in several ways. It was used to help narrow the scope of the project because we had too many conflicting ideas, interpret unexpected results, explain some of the stranger results that we were seeing, and also consolidate results into a concise format.